We've been having these for the past month or so every 2 weeks, and for the last couple times, and today we're honoring our recent Physical Chemistry Division awardees. And so with us moderating today, we have Carlos Baiz from the University of Texas, and we have Rodrigo Noriega from Utah. And the format here, before I get into the introductions and turn everything over to Professor Hartland, is that we are going to moderate the questions and answers in the chat function. And after Professor Hartland's finished, the moderators will take turns asking your questions. And then after that, we will, after everyone has a chance to ask their questions through the moderators, then we will kick all of the faculty out and invite just the graduate students and postdocs to remain and to have a chance to ask your questions one-on-one to Professor Hartland. And so with that, I'd like to introduce Professor Greg Hartland. He's from Notre Dame, and he is a professor there, and he's also the chair of graduate studies, which is a very brave job. And additionally, he's a senior editor, deputy editor. Is that the correct word? There's so many deputy editor, the Journal of Physical Chemistry. And he is the senior experimental chemistry awardee of the Physical Chemistry Division this past year. And you can see the title of his talk here. And so I'm not going to take any more time away from his talk and just turn it over. Greg, you can go ahead and share, and we look forward to your talk.
All right, well, thank you very much for the introduction, and for Christy and Carlos and Rodrigo for helping organize this. It's an honor for me to give the talk today and to have won the award, so I very much appreciate that. And I'm going to talk about work that we've been doing, for the last couple of decades on looking at plasmonic or metal nanostructures, and it'll mostly be single particle experiments. Okay, so this slide is a sort of an overview of the sort of things that we're doing in our group. We are interested in surface plasmons and the vibrations of metal nanostructures, and also using ultrafast spectroscopy. And of course, we use ultrafast spectroscopy to look at these vibrations. And we also have projects in developing ways to image nanomaterials. But in the talk today, I'm mainly going to be talking about surface plasmons and the nanostructure vibrations. So because these experiments involve metals and the interaction of metals with light, it's helpful for me, and hopefully to everyone else, to start with a sort of a cartoon of the processes that occur when you shine light at a metal nanostructure. Okay, and so these are little images. They are basically cartoons of generated in COMSOL of the interaction of light with metals. So we think about this as the photons excite the plasmon resonances of the particles, or the structures that you're looking at, and the plasmons are collective motions of the electrons. So that collective motion, that dipole that gets induced by the light, that oscillates for about a timescale of about 10 femtoseconds before it dephases. Okay, and that dephasing process creates hot electrons in the metal nanostructure. And those electrons are distributed in space in a way that depends on the internal electric fields in the structure. And they're distributed over a fairly wide range of energy after that initial absorption of a photon. Okay, so these hot electrons, which are of currently a lot of interest right in photocatalysis, they interact amongst themselves and redistribute this energy to create a Fermi distribution at some high temperature. And so that process is this electron-electron coupling, and that happens in about 100 femtoseconds, so about 10 times faster than this initial dephasing of the plasmon. Okay, you create a you can create a very high temperature of the electrons. When you do that, the electrons now are not at equilibrium, right, with the lattice, with the atomic motions in the particle. And so the electrons will exchange energy with the phonons. And that process, electron-phonon coupling, takes a few picoseconds. And when that's over, the electrons and the lattice are at the same temperature. And if you start with put enough energy in to create a temperature of the electrons of about 900 Kelvin. When they reach equilibrium with the phonons, you'll get about a 10 Kelvin temperature rise in the lattice. So this is my sort of very quick picture of what happens with the interaction of light with metals. Okay, so you get this very rapid heating of the lattice, and the temperatures that you create are on the order of a few Kelvin to tens of Kelvin in typical experiments. So when you heat up a metal, heat the lattice, it will want to expand, right? Everything wants to expand when you heat it up. And because the heating process is so quick, it's faster, almost invariably faster than the coordinates or the vibrational modes that correspond with the expansion process. So these are the breathing modes of the particle. And this is a situation where you can coherently excite these breathing modes. And so that's one of the major things that we see in the experiment. And this is, again, a cartoon of some breathing modes in COMSOL. And then those modes will lose energy into the environment, right, by coupling to whatever they're around. So this talk, I'm going to concentrate on the processes at the start, the dephasing of the plasmon, and at the end, how these vibrational modes lose energy to their environment, and sort of not worry too much about this stuff in the middle, okay? And because it's, we're focusing on lifetimes, right? We're going to measure the lifetimes or look at the lifetimes of the plasmons and the lifetimes of the vibrations. It turns out when you do an experiment on a sample of metal nanostructures that you might make or buy, right, there's a whole bunch of different sizes in that sample. So the lifetimes sort of suffer from inhomogeneous broadening. So if you want to get accurate information about the lifetimes, you really ought to do single particle experiments. And that's going to be a big part of the talk. Okay, so let's start off with discussing what happens to the dephasing of the plasmons. Right, so this is a very, very fast process, and it's really right at the edge or even beyond what you could do, what you could measure just through ultra-fast spectroscopy. Okay, so the way to get lifetime information when you look at the plasmons is to actually measure a spectrum of a single particle, and then the width of the spectrum will give you information about the lifetime. So these are some example spectra taken by the Lyon group, Fabrice Vallée and his colleagues at Lyon, and also by Stefan and some of his colleagues. I think the experiments were done in Germany. So what you see here are these are some measurements on single particles. We're looking at a plasmon resonance for particles. That's commonly called the localized surface plasmon resonance. And you can measure the frequency or the wavelength of the resonance and its width. There are a couple of different ways of doing that. The most common ways are to do these spatial modulation experiments that are over here on my left or your left, right, where you modulate the sample in and out of a focused laser beam, and you use that to record a signal and change the wavelength to get a spectrum. You can also do these sort of experiments through light scattering. That's actually a little bit easier typically, where you just look at the scattered light from a single particle, and again, you can find a resonance, you get the resonance frequency and the line width, and the line width would tell you about the time scale for the dephasing of the plasmon. Right, and these experiments, these line widths are, well, they're on the order of 100 millieV, which would be about a dephasing time of around about 15 femtoseconds, right, so very fast. Okay, so I'm actually not going to talk about localized plasmon resonances, although we've done a little bit of this work. I'm going to talk about the other type of plasmons, which are propagating plasmons. So if you have an extended metal nanostructure like a film or a nanowire or a nanoplate, you can also have plasmons that move along the surface of these structures, and these plasmons have a definite momentum. So one thing that does, because they have momentum, is that it means that it's a little tricky sometimes to couple light to the motion of the electrons because you have to match momentum. So one way that you can conveniently do that is to look at a nanowire or a nanoplate under a microscope and focus your laser beam at the end of the nanowire or the edge of the plate where the break-in symmetry relaxes the momentum matching considerations, and then you can excite these plasmon modes. So if we look at the wires up here, this is what we've done. These are actually two different wires. Don't worry about the image in the middle. These are the ones on the sides of the scattered light images of what I want to talk about. Okay, so if you look at this wire, we focus the laser at the end of the wire, we excite a plasmon mode. These are nanowires that are on a glass surface. So there are two modes. There's one mode that moves along the top of the wire at the metal air interface, and there's another mode that moves along the bottom at the metal glass interface, and they have different wave vectors, different momentum characteristics. Okay, so the one that moves at the metal glass interface has a fairly large wave vector, and so it can't couple to photons in the substrate. So for this mode, what happens is you excite the plasmon, it moves down the wire. When it gets to the other end of the wire, there's again a break in the symmetry and a little bit of light comes out. The other type of mode has a much smaller effective index slash wave vector. So for this mode that moves along the top of the surface, that can couple to photons in the glass. And so when you image that wire, you can see some light as the plasmon moves down the wire, right? And this is called a leaky mode. Okay, so these are the two different plasmon modes that happen in a wire. These images over here at the bottom are the same sort of thing for some nanoplates. So you have a laser focused on the edge and you can excite plasmon modes in the nanoplate that move across the plate. When they get to the edges, they emit a bit of light. Okay, so for a resonance, what you measure are a resonance frequency and a line width, and the line width gives you the lifetime information. For these propagating modes, what you can measure are the propagation length and the wave vector. And it turns out if you take those two measurements, you can also get lifetime information. So when you look at these images like this one here, where you have a leaky mode, right, you can get the propagation length just by looking at the light coming off that wire and how the intensity decays as you go down the wire. And that will give you the propagation length. But to get the lifetime, you also need to get the wave vector. And to do that, we use a little trick in optics. So what happens in a microscope, right, is that you have an objective, a lens that collimates light coming off from the sample. And then in this sort of image here, or these images over here, which are called real space images, you send that light to a camera and you put a lens in front of the camera and the lens forms an image on the camera. So if you look up an optics book in the chapter on Fourier optics, they'll describe that process as the lens does a spatial Fourier transform to create the image. And so that's a sort of fancy way of saying things, but what it means is that if you take that lens out, you do a Fourier transform of your image. And when you do that, you can measure the wave vector of the plasmon. So these images over here are regular real space images where we have the lens in front of the camera and we look at what things look like in actual space. And on the right here, we have Fourier space images where we take the lens out, and that allows us to measure the wave vector. So you can see this line here, that is the wave vector of the plasmon. So you can get that out of the image. For the plate here, you see an arc rather than a line, and simply that's because you have plasmons that are sort of moving off in different directions, right, for a plate when you excite in the edge, and so you have a bunch of different wave vectors along here. And in either case, you can measure the wave vector. Okay, and I'll show you how that gives you the lifetime information in a second. I just want to point out, though, that these propagation lengths, and mainly the propagation lengths, very sensitive to the thickness and the shape of the materials. So to do a proper study, what one ought to do is have good control over those parameters. So rather than sort of use chemically synthesized materials, what we did here is we did some photolithography to make structures that all had about the same thickness, and that makes the experiment a lot easier. So these are some images of our structures. We call them nanostripes. They're about 50 nanometers thick. They have different widths and they're all about 100 microns long, right? So they're really long. The length doesn't matter here. So we focus our laser beam at the end of the structure to excite propagating plasmon modes to scoot on down the structure. We're just looking at light scattering, so we're only measuring the leaky modes, the ones that are at the top of the structure. And then we take a real space image, which is either here or these images here, to measure the propagation length. And then we flip out the lens and we do a Fourier space image to get the wave vector. Okay, and you can sort of see there's a couple of wave vector diagrams here. If we collect light from the whole structure, we get these arcs again because the plasmons are moving off in different directions right at the start here. If we limit our collection to just this sort of red triangle area here sort of lower down the wire. Now everything's kind of moving in the same direction and we get lines again. And either way, we can measure the wave vector. Okay, so what we do is we do this experiment. We measure the wave vector for a bunch of frequencies, and then we plot that as frequency versus wave vector to generate a dispersion curve. And so the lifetime of the plasmon is given as the propagation length divided by the group velocity. And the group velocity is just the speed, is the slope of that dispersion curve. So you see we need both the propagation length and the wave vector information to get the lifetime, right? So we measure a bunch of frequencies to get this speed. So this is an example for a nanostripe that had a width of 4 microns. The green dots are our experiments. For that size structure, there are actually a bunch of different leaky modes. They have different orders. So these are plots of what those modes look like generated in COMSOL. And so these red lines here are the dispersion curves for all these different leaky modes, right? So you can see a bunch of them. We mainly seem to see this lowest order mode. Maybe it has something to do with the overlap of the laser with the form of the modes. So in any event, right, we do this measurement. We get a group velocity that's about almost 90% of the speed of light, right? So these things move very, very fast down the wire. The propagation length is about 12 microns. And so when we take these two measurements, we work out a lifetime of about 47 femtoseconds, right? So actually still really, really fast, okay? But almost 5 times slower or longer than what you get for the gold nanorods. So if you think about lifetime for the localized plasmon resonances in nanostructures, they're much shorter. So these motions have, at least the leaky mode, can have much longer lifetimes. All right, so that's sort of interesting. Maybe that would be useful for measuring things. And so this is sort of now a plot of these lifetime measurements for a bunch of rods or nanostripes with different widths. So the red points up here are the experimental measurements, and the blue line is a calculation, again, from COMSOL of what the lifetime should be. So we get a pretty good match between the experiments and the calculations, which is nice. Now, one of the nice things in COMSOL or in calculations is that you can actually pick apart the different contributions. So the lifetime of these modes should be controlled by 2 things. One is that as these modes move, they create electrons, hot electrons, and that's a decay process. That's sort of, might call that a resistive heating process. The other thing is that they radiate, right? They give off photons as they move down the wire. So that's the radiation damping. So in COMSOL, you can work out the relative contributions from those 2 parts. And that's what's done here. This is plot of an attenuation rather than the lifetime. So it's essentially the inverse of the lifetime. This is done for nanostripes that have different widths. So I think 2, 4, and 8. Actually, the 2 is at the top, the 4, and then the 8, and also different thicknesses. Okay, so what this plot shows is that the attenuation gets much stronger as you make the nanostripes smaller, either as you make them thinner or as you make them, as you reduce the width. Okay, so you reduce the dimensions, the lifetimes go down. And that's what we see here, right? That the lifetimes go down as you make these things, as you reduce the width. The strange thing, or at least it was strange to me about this, is that when you look at that effect, you see that that increase in attenuation / reduction in lifetime comes about because of increased radiation damping, right? These, for the smaller structures, they're more lossy, they give off photons more easy. And what's strange about that is that for particles, radiation damping is larger when the structures are larger, not smaller. Here we see it's the opposite effect. Radiation damping is larger when the structures get thin or has small dimensions rather than large dimensions. And it just sort of seems like we can understand that through a geometric effect, that as we make the structure smaller and smaller, the field from the plasmon that's moving at the top of the structure, or the field at the top of the structure, sort of gets more intimately involved with the photonic fields in the glass. So it sort of leaks over into the glass more, and you get better coupling with photon modes in the glass, and so the structures become a bit leakier as they get smaller. It's in the opposite direction of what happens for a particle. Because these things have very long lifetimes, we thought that maybe we could measure the properties of metal surfaces accurately. So one thing that's of interest is to measure chemical interface damping, right? If you put a molecule on the surface of the metal nanostructure, you damp the plasmons. This has been looked at quite a bit for particles, and so we tried to do the same thing for the nanostripes. And so if we take one of our nanostripes and we add an alkane thiol, we do see that the propagation length goes down. So we see an interaction with the molecules, and we can analyze that to get a effect damping from the molecules, which we call chemical interface damping. And it turns out that it's a very small effect, right? If you look at particles that Stefan did with Carsten Sonneschen a few years ago, chemical interface damping is about 20 to 30 millieV. We're about 10 times, 20 times smaller than that. And the reason is that these structures are very large, so the surface to volume ratio is not very good, right? The metal particles that you look at are much smaller, so the surface is a much bigger effect, and chemical interface damping is bigger. These structures are too big to give you much chemical interface damping. And our problem is that we can't make the structures smaller and get higher chemical interface damping, because if we do that, we get more radiation damping and we can't measure anything, right? So the signal goes away. So that's sort of where we ended up with this project. Okay, so the next part I want to talk about are these vibrational modes, which we've been looking at for a long time, and in fact goes back to when Stefan was with Mustafa, right? We're talking about these vibrational modes that you see. So when you shine an ultra-fast laser pulse at a metal particle, you get this fast heating and you excite the breathing modes. And so this is a transient absorption experiment. This is time versus wavelength for a gold nanoparticle sample in water. And you can sort of see these little oscillations here that come about from the breathing modes. And so you see them in the transient absorption spectrum because as you have this breathing motion, you know, the particles change size a little bit. So there's a change in the electron density. And that change in the electron density moves the plasmon band back and forth a little bit. And that gives you the signal in the transient absorption experiment. So if we look at a wavelength versus, or the signal at a single wavelength, this one's at 550 nanometers, somewhere in here. You can see these oscillations that are the breathing mode. You can fit that to a cosine to get both the frequency and the damping time. And we usually express the damping times in terms of a quality factor, which is essentially the lifetime divided by the period. Okay, so this sample has a quality factor of about 4. That's pretty lousy, and it's because in the sample there's a whole bunch of different size particles. Each one of those particles has a different period. When you add up all those periods, you get a damping in the ensemble measurement. Okay, you can calculate the frequency either using analytic expressions if they're available, or again doing finite element simulations. So for a finite element simulation of a 40 nanometer particle, you predict a frequency of about 76 gigahertz, right? So it's basically matches what you expect from continuum mechanics exactly. There's also an analytic expression that comes from this wonderful paper by Horace Lamb in 1882, well over 100 years ago, where he worked out an eigenvalue equation for the frequency of the breathing mode. In this paper, he was interested in working out the period of the breathing mode of the Earth. And if I remember rightly, it's about 2 hours, right? So it's very kind of nice old paper. And if you use the speeds of sound for gold and this formula that Lamb developed for planets, you get the right answer, right? You get the same answer. Okay, so our goal is to try and measure the lifetime of these modes. And I think it's pretty obvious that for this sample, which is actually not a very good one, it has a size distribution of about 10%. That's not all that great. You can't get lifetime information. The damping is dominated by the size distribution. If you have very, very, very well-made samples of very narrow size distributions, you might be able to measure a lifetime. But the other way of doing it, of course, is just to look at a single particle. Okay, and so that's what we set out to do, and this is sort of how we do that experiment. And so this is a cartoon, again, lots of cartoons. It's a picture of basically the size of a diffraction limited laser beam of green light at a sample compared to a 20 nanometer diameter metal particle, right? Can you see that the laser beam is going to be much, much, much larger than the particle? So luckily for us and for many applications, right, metal particles absorb very strongly. So they absorb more than just their geometrical cross section. So a 20 nanometer particle with green light will, if you have a diffraction limited experiment, that particle will absorb about 1% of the light. Okay, not much, but actually, it's measurable. We're doing transient absorption experiments. So transient absorption experiments, the signal levels are typically about 1,000 times smaller than the linear absorption measurements. So you'd expect a single metal particle to give you a transient absorption signal of about 10 to the minus 4, 10 to the minus 5, right? That would be the change in the transmission. Okay, so that's very small. But if you have a very stable high frequency laser system and you do tricks like high frequency modulation, you can measure signals as small as 10 to the minus 7 or so in differential transmission. So that's sufficient to detect and study single particles that have dimensions on the order of 10 nanometers. Okay, you can, it's, not, if you have the right laser system, it's not that hard to see a single particle. You just have to have a stable laser and focus very tightly. And you do need to do high frequency modulation to get the signal out of the noise. Okay, so that's what we do. These are some images of actually the only images I'll show of some semiconductors. This is semiconductor nanowires made by my colleague Ken Kuno. These images were recorded by overlapping the pump and probe at the sample and then scanning the sample through the laser beam to make an image. And the point of this experiment was that what we did here is we recorded images at different powers of the probe. And when we do that, we see that signal to noise increases. And if you think about that a little bit, it means that you're shot noise limited. Okay, that the fluctuations of the laser are not determining the noise in the experiment, it's only how many photons you count. So if you have a very high frequency laser pulse and you count lots of photons, you can get enough signal to make an image and study the nano object. This is not the only way you can make an image. I'll show you another way of doing it. You can also do an experiment where you focus the pump at a point in the sample and then you scan the probe around the pump. Usually one does that by just moving some mirrors to make the pump, or the probe, I should say, go to different positions. I'll show an example of that image. That scanning modality is used a lot for people who study semiconductors to look at exciton motions. Okay, so this is at the bottom here, we have a sort of really it's just a partial list of people who do these sort of measurements of single nanostructures. What's a little bit strange about it, I suppose, is we do almost all the metals, and it seems like in Europe, everyone does metals, with the exception of Stefan, who's actually Stefan's in Europe right now, right? In the US, almost everybody looks at semiconductors, right? So I'm going to talk about metals, so I'll be a honorary European today. Okay, so this is an example of that other sort of imaging where you focus the pump laser at a spot in the sample, and then you scan the probe to make an image. And this is, again, of the plasmon modes of a single nanoplate. So our pump is focused at this point in the plate. We scan the probe around the structure and we get an image. Okay, and the most striking thing about this image, of course, is that you can see that there are these waves emanating out from where we excited the sample. So what's happening here is, again, when we hit the edge of the plate, we excite propagating plasmon modes. We have two of them. We have the bound mode at the metal glass interface and the leaky mode at the metal air interface. And they have different wave vectors. So as they move away from the excitation region or away from along the plate, right, they interfere with each other. That interference creates this wave-like structure in the image. Right, so we're looking at the interference between the bound and leaky modes. And so this is a sort of a slice down one direction of this plate. And this wavelength depends on the difference in the wave vectors of the bound and leaky modes, and we can calculate that. We get almost perfect agreement with what we measure. If we do our little trick of Fourier space imaging to measure the wave vector of the leaky mode, right, we can then from this measurement get the wave vector of the bound mode, which is actually not that easy to do. And that's what's done over here. The blue dots are the leaky mode from these Fourier plane images, the red dots are the bound mode. And so we can measure both of them, the lines of the calculations. Don't worry about the green dots, they didn't work too well. Okay, so what we'll be talking about, from most of the talk now is the vibrational modes of these structures and how they depend on their environment. And so this is a slide taken from a fairly recent paper, again from the Lyon group, Fabrice Vallée, Natalia Delfatti, on some lithographically made structures. So structures that are really kind of stuck pretty hard onto the surface. Okay, you see oscillations here, that's the breathing modes. And in these experiments, what they did is that they changed the aspect ratio, the width compared to the diameter of these little structures that they made. And so what I want to focus on is the lifetime, again, expressed as a quality factor, basically the lifetime divided by the period. And so what you see in general is you get quality factors of about between 10 and 20. Okay, and so this is sort of typical of a structure that's stuck onto a metal surface. These are very similar to the numbers that Stefan's measured in his lab. And so what's happening here is that you're kind of losing energy. You have sound waves radiating into the glass or the support of the structure, and that's taking the energy away, and that's what's causing the damping. And so this is sort of like a radiation damping, like what you get in optics, right? But it's radiation of sound waves. The interesting thing about the Vallée and Delfatti, or the measurements in this paper, maybe to be more polite to say it that way, is that you can see at certain aspect ratios, there's a big increase in the quality factor. So what's happened here is that at specific aspect ratios, and this effect is reproduced in these calculations down here. So for some aspect ratios here, the modes that you're interrogating in the experiment are sort of just stuck up on the top surface of the structure, and they're not coupling very efficiently to the substrate. So you've sort of managed to reduce the amount of radiation damping for these modes just by controlling their shape. And so in that case, you can get structures that have very high, larger quality factors, right? 70 to 80, right? Which really starts to become quite large. For localized plasmon resonances, you kind of have a bit of an analogous effect. You can change shape and make dark modes that don't couple very effectively to light, and they can have narrow resonances. A sort of trivial example of that is a quadrupole mode. Right? And so you can sort of do the same thing with acoustic modes, control radiation damping by controlling their shape. However, for acoustic modes, there's actually a much easier way to do that, and that's just simply to get rid of the substrate. So these are some examples of some nanowires where we've made substrates where we've cut little trenches in them and then just dropped some nanowires onto that substrate, and some of them end up hanging over the trenches. And then if we look in the region over the trench, we have a material that's not going to lose its energy by radiating sound waves, because there's nothing to radiate the sound waves to, right? It's just air. So the experiment on the left is for a very large structure, and we did this so that we could measure the dimensions of the structure by SEM. That's what it looks like. It's a pentagonal structure, sort of typical with gold nanorods that you make by chemical means. For a pentagonal structure, you get two breathing modes, one where you have basically motion at the apexes of the structure, and another one where you have motion at the faces of the structure. They have different frequencies. This is the transient absorption trace, where you clearly see two vibrational modes that are going in and out of phase. We measure the frequencies, and then we can calculate what we expect them to be based on the dimensions we got in the SEM, and we get extremely good match between the measured and calculated vibrational frequency. Okay. In general, we like to look at much smaller structures. With smaller structures, we can't see them by SEM. So we don't know their dimensions, we just measure their frequencies. And so these are some examples over on the right here of traces for some smaller structures, much higher frequencies. These are again nanowires. You see these two frequencies going in and out of phase, one in air, and then in this experiment, we put this structure in water, and you can see that the modes are damped by the interaction with the liquid. Okay, so if I have time, I want to talk about three things about these vibrational modes. One is liquid damping and measuring the how liquids take energy away from these structures. The other one is vibrational coupling between two different structures. If you put two structures close together, how do their vibrations couple? And the third one is what happens when you add mass or take mass away from the structures. And for all of those structures, it's nice to have nanomaterials that have very, very long-lived vibrations, right? The longer the vibrations go on, the more accurately you can measure the quality factors and the more accurately you can measure the frequency. So that's good for all of those applications. And so for us, the best structures to look at are not little nanowires. It's actually to look at these nanoplates. And again, to do a trick of either supporting the nanoplates over a trench so that they are not in contact with anything, or it turns out you can also put the nanoplates on a very light substrate like a carbon TEM grid, and then you also don't get any effect from radiation damping. You get very long lifetimes. So this is how we do it in our laboratory, and these are some experiments done by my collaborator Kuai Yu in China, where they use TEM grids to look at the structures. And I'll show some nice data from Kuai's lab in a little bit. Okay, so for this gold plate here, that's suspended over a trench that's been cut into a substrate. Right now, you can sort of see a very, very long-lived vibrations, quality factors of over 100, right? So really quite long. So we can measure this frequency really accurately. These are some experiments by Kuai on these carbon supports. On the support, you can get quality factors of about 100 to 200, average of about 180. So very, very large quality factors. The red lines here are for these same, nanoplates out of the same sample on a glass substrate, quality factors on the order of 10. Again, typical of what you measure if you have something on a solid substrate, quite low, strong damping, loss of energy by sound waves going into the substrate, and small quality factors. Whereas if you have them on light substrates or suspended, you get much larger quality factors. Okay, so the first thing to talk about is the interaction with liquids. And just skipping back, what we do in these experiments is that we measure the lifetimes or quality factors in air. We add a liquid and we come back and measure the lifetimes and quality factors of the same nanostructure in the liquid. And the difference between those two measurements tells us about the liquid. And the reason to do this, which was motivated by my collaborator in Australia, John Sader, who's worked with almost anyone who does stuff with vibrations and nanostructures, was to try and explore viscoelasticity. Okay, so just to give you viscoelasticity for a lot of experimental physical chemists isn't all that common a concept. So I'll just sort of give a very quick introduction to it. Okay, so viscoelasticity is the effect of having a non-Newtonian liquid. We actually, anyone who's been to a junior high science fair would have come across a non-Newtonian liquid, right? So if you mix cornstarch and water, you get a non-Newtonian liquid. And so if you make that mixture, like if you have kids and you make that mixture, well, you can go home and do it yourself, right? If you stick your finger in it slowly, it feels like a liquid, but if you punch it, it feels like a solid. So the way it behaves or the way it sort of feels or reacts is a question of the frequency of the experiment, either doing something at low frequency or high frequency compared to the relaxation time of the structure of the material. So it turns out that that question, whether something behaves like a solid or a liquid, is just a question of relaxation time, right? So, and that is captured in what's called the Deborah number, which is a parameter that was invented by a rheologist who's also a biblical scholar, right? So the Deborah number is the frequency times the relaxation time. Things that have long relaxation times or experiments that are done at very low frequencies have behaved like a solid. Experiments done at very, did I say that the right way? Maybe not. Oh boy, I'm going to confuse myself now. So things that are done at low frequency, if you do things at low frequency or you have, fast relaxation times, to restate that, it will behave like a liquid. Whereas if you do things at high frequencies or you have long relaxation times, it will behave like a solid. Okay, so the idea of the Deborah number is that it's a quote from Old Testament that the mountains flowed before the Lord by the prophet Deborah. So on human time scales, which are short time scales, high frequencies, mountains look like solids, but on very, very long time scales, which is the time scales of the Lord, right, mountains would behave like liquids, right? So that's where the idea of the Deborah number comes about. And so whether things behave like a solid or a liquid is a comparison of these two parameters. So if you go to very high frequencies, even if you have things with short relaxation times, they should start behaving, have solid-like properties. That's viscoelasticity. So the idea of these experiments was that if you have a nanostructure, the breathing modes of nanostructures, they are very high frequency if you make the dimensions of the structure small enough. So we hoped that we would be able to see viscoelasticity in simple liquids if we could make the frequencies high enough, even liquids that had short relaxation times. Okay, and so to do this experiment, you need to have large quality factors so you can measure things accurately, and you need to have very high frequencies. And so this is some experiments. The experiments were done by Kwai, and if you can believe that, I did the theory. And so these are some very thin nanoplates that have very high frequencies and high quality factors. And so what Kwai did in these experiments is he measured the frequencies and quality factors in air. Then he added different liquids, different water glycerol mixtures, and looked at the damping and worked out a quality factor for liquid damping. And then we compare that to this calculation to see if we can see viscoelastic effects. Okay, and so in this calculation, you write down the equations of motion of the solid and liquid, you match the stress and velocity at the interfaces, and you can generate an eigenvalue equation that will give you the frequency of the vibrational mode. And there's a real and imaginary part, and the imaginary part gives you the damping, the real part gives you the frequency. Okay, so this equation has the densities of the solid, the densities and speeds of sound of the solid and the liquid. It has the viscosity of the liquid in this beta parameter. So you can, if you leave out viscosity, then you just have the liquid like it was a solid. You can add viscosity by including beta, and you can add viscoelasticity, include the relaxation time by modeling the viscosity of the liquid in this way. This is called a Maxwell model. This includes the relaxation time. So you put all this stuff in, and then you compare this to the experimental measurements to see if you can detect viscoelastic effects. All right, and so this is the result of the calculation. The lines are these different calculations. The solid line is leaving viscosity out, so the liquid just has a density and the speed of sound. The green line is including viscosity, but leaving out the relaxation time, so leaving out viscoelastic effects. So this is a Newtonian liquid, and the blue line is including everything. So these little boxes are our experimental measurements for these very high frequency vibrations of the thin nanoplates at about 100 gigahertz. So if you have water, right, you can see the experiments, both the viscous and the viscoelastic models of the liquid match the experimental results. Another way of saying that is that we can't really see any effect from viscoelasticity for water at these frequencies. Okay? If we go to a very viscous liquid like glycerol, then you can see that there's a clear difference now between the predictions of models with viscoelasticity and without viscoelasticity, and that our experimental results match the viscoelastic model quite well, right? They don't match the inviscid model where you leave out viscosity. So we can, maybe a better way of doing this experiment is to just take our quality factors that we measure and then using the equations to fit to determine a relaxation time. And so that's what's done here. These black dots are the relaxation times from the experiments of the nanoplate vibrations in different liquids. These are all water glycerol mixtures with different weight percents of glycerol. And so we measure relaxation times going from hundreds of picoseconds down to about a picosecond for just pure water. The solid line here is the literature values for the relaxation time. And then the red line, or the red experiments, is from the Brion oscillations. And I forgot to mention those. I'm sorry, I'll go back. You see these long oscillations here? Okay. These long time oscillations are what we call Brion oscillations. That when you have a metal nanostructure in a liquid, right, you hit it with a laser pulse, it will generate sound waves in the liquid. And the Brion oscillations are a reflection interference phenomena from light that's reflected from the metal and from those sound waves. Okay, and the frequency depends on the speed of sound in the liquid, and also the refractive index and wavelength of the probe laser. Okay, so this is what these are. So it turns out, because these Brillouin oscillations involve the speed of sound in the liquid, they also are sensitive to viscoelastic effects. And so you can also estimate the time scale from the Brillouin oscillations. And so everything's actually really in pretty good agreement. So we can see, because of these high frequencies that we make with these nanomaterials, we see viscoelastic effects, and we can use that to measure a relaxation time for the liquid. So one of the questions is, well, you know, the experiments that I showed at the start were introduced, the vibrations were on an ensemble. Well, can you do the same thing if you just are a lot more careful about your sample? Okay, so if you get a sample of metal particles that has a very narrow size distribution, can you see effects from viscoelasticity? So the answer is yes, it's possible, right? You can get metal nanoparticle samples that have standard deviations that are really very narrow. This sample here is about standard deviations about 4 times narrower than what I had in my sample. And so in that case, you get quality factors that are about 4 times larger. And this is work recently done by Matt Pelton and published in JPCL. And so quality factors were about 16, where we were measuring about 4, and there's a factor difference of 4 in the size distribution. And that's now good enough when you put these particles into different liquids with different viscosities, that you can see effects from viscoelasticity. So the red line here, or the blue markers, are the experimental measurements. The red line is the viscoelastic model of the liquid, and the green line is the Newtonian, leaving out the relaxation time. So you can see clearly at high percentages of glycerol an effect from viscoelasticity, like what we saw for the plates. Okay, so let me talk about 2 more things that you can do with the nanostructures if you have very high quality factors. One of them is to look at coupling, right? So these are some experiments. Again, the experiments were done by Kwai of plates that, when you drop cast nanoplates onto a sample, sometimes some of them overlap, right? So this is an image of 2 overlap plates. And in that case, you can do an experiment where you excite the plate here, or this plate here, or you can excite in the overlap region. Okay, when you excite either of the single plates, you see a single frequency. Okay, that's the breathing mode, and that depends on the thickness of the plate. And when you're in the overlap region here, right, you see a much more complicated pattern, right? So you have multiple frequencies. These are the Fourier transforms. So the blue and greenish curves are the non-overlap single plate regions. You see a single frequency corresponding to the breathing mode. In the overlap region, you again see 2 frequencies up in this spectral region, but they're shifted because the 2 vibrations are coupling to each other. There's also a lower frequency mode. We call that the relative mode. That is the 2 plates just vibrating relative to each other. It's not the breathing mode, it's the plates moving independently of each other. So you see a vibrational coupling. And if we look at the data down here, this is a plot of the shift in the frequencies for a whole bunch of different plates that have different initial vibrational frequencies. And so this delta 1, 2 is the difference between the 2 initial frequencies, right? So at this end, delta 1, 2 being 0, we have 2 plates that have very similar frequencies. Over here at this region, they have very different frequencies. And if you look at the shifted frequencies, right, you see essentially an avoided crossing type effect. There are big shifts when the frequencies are close together, strong coupling, and when the frequencies are far apart, right, there's very small shifts. So this is a classic example of an avoided crossing in a 2-level system, right? There's coupling between the 2 vibrations that cause a shift in the frequencies when the 2 plates are overlapped with each other. If we use this data to work out a coupling constant, we get about 8 gigahertz, and that's right, really very strong coupling, right? Because the frequencies are about less than 80 gigahertz in these experiments. So the coupling between them is over 10% of the actual frequency. So these are very strongly coupled systems. So sort of interesting in that. And it's an example of sort of a classical mechanics example of a strongly coupled 2-level system. The other thing that we can do with these resonators that have very high quality factors is we can look at what happens to the frequencies when we add or subtract mass. So the top graph here is some plots of frequencies for some nanoplates before and after plasma cleaning. So plasma cleaning, for us, it was meant to just take off all the organic material that's on top of the plates, right? When you make these plates in solution, they are coated in surfactant. So if we remove the surfactant, what we see is that there's always an increase in the frequency. So this is sort of a mass loading effect, right? When we take mass off the plates by cleaning them, the frequency goes up. Okay, and so these are the experimental results calculated as a relative difference in the frequency versus the frequency of the vibration. And the different lines here are calculations for what would happen if we remove different thicknesses of organic material from the surface. So our experimental results are consistent with removing about 3 to 5 nanometers of organic material, and that's about the thickness of a bilayer of CTAB, which is what these things were coated in. So that seems to make sense. Okay, this is a bit more interesting mass loading experiment. This is a nanoplate where we have tried to coat with some polystyrene beads. So you can see the plate here, and these little circles here are the polystyrene beads. So what we did in this experiment is we did measurements where we focused, or rather Tufan did measurements where he focused the laser in the region of the plate where there are no beads. And then he did an experiment where he focused the laser on a region of the plate where there are beads. Right, so no matter where you go in the plate, if there are no beads, you always kind of measure the same frequency. These materials are very, very uniform. When you go onto the beads, you measure a different frequency and it is shifted to a lower frequency. So there's, again, a mass loading effect that comes about from adding the beads to the plates. I think this is sort of a little surprising to me because, well, basically, you know, the vibrational mode, the breathing mode, is a normal mode of the plate, right? So it has amplitude all over the plate, but we're seeing different frequencies in different spatial regions. So there must be some hybridization that's going on caused by the beads that causes a localized mode here and modes that are different in different regions of the plate. So this is actually, I think, more complicated than just what this experiment might look like. All right, so I think I'm coming pretty much to the end of the time. So I'm going to sort of skip over this last bit. So apologies to anyone who's interested in this. You can ask me about it, I suppose, and just go to the conclusion. So, you know, maybe the theme of this talk is to talk about radiation damping. In the start, for plasmons, right, radiation damping is sort of pretty well known, right? If you have large particles, they lose, the plasmon loses energy by scattering light, by giving off photons. You also have radiation damping for these propagating plasmon modes. And the thing that was unusual about this, to me anyway, was that for these propagating plasmon modes, radiation damping gets bigger when the structures get smaller. And for localized plasmon modes, it's exactly the opposite. Radiation damping gets bigger when the structures get bigger. For the acoustic modes, there's a large energy loss mechanism from radiation damping, from sound waves radiating out into the substrate. We can get rid of that effect by suspending the structures, and then you can create materials that have very long lifetime vibrational modes. And that allows us to look at processes like coupling between nanostructures and mass loading effects. And also when we go to very small, thin nanoplates that have very high frequencies, the long lifetimes help us measure viscoelastic effects in liquids and to show that they occur at the nanoscale. So for nanoscale materials, right, liquids behave quite differently than what they do for macroscale materials because of these the high frequencies they encounter. And then let me just thank you know, the people who've done the work, mostly Tufan, Gary, Brendan, and Cameron, and we've benefited a lot from collaborations both at Notre Dame with John Camden, Ken Kuno, and Jean Kamat, and also with theoreticians David and John, and of course Kwai, who's done a lot of work. With that, I'll end, and thank you for spending your Friday afternoon with me.
Well, thank you, Professor Hartland. That was a very interesting talk. Very, very different from our previous talks.
Yeah.
And we have a few questions actually, and I just want to remind the audience that please use the chat function and type in your question, and we will ask your question to Professor Hartland. So the first question we have is actually from Stefan. asking, will the lifetime of the propagating modes be longer if you prepare single crystalline nanowires instead of nanostripes? And then another question, a follow-up question, would it be easier to measure the CID with them?
The follow-up question is that I don't think it will be easier to measure CID. I think you'll still run into the problem that we need to measure the wave vector and the propagation length. And if you make the structures too small, the propagation lengths get too small and they just become hard to measure. So the thing about the particles, one of the reasons that experiment works, right, is that when you make the structures smaller, you get more CID and you get rid of radiation damping. When we make the structures smaller, we get more radiation damping. So they compete, right? So it's better to look at radiation damping in the particles. The other part of Stefan's question, I guess I'll have to stop sharing my screen. I'll have to go back and share it.
I don't think you're sharing right now.
That's right. Yeah. Is that okay? You can see that now?
Yeah.
Okay. So the other part of Stefan's question about if you had single crystal plates, I think there's a feeling, everyone has this feeling, that if you made the structures single crystalline, right, that the damping would be less, right? You wouldn't have grain boundaries. And the facetious answer to that is that what everyone does is they make a structure and then they measure a damping or they measure a line width, and then they compare it to Johnson and Christie's data, right? Johnson and Christie's data was done for polycrystalline films. So, if you match Johnson and Christie's data, it kind of shows that, maybe polycrystallinity isn't a very big effect. And though it actually did occur, this is what I did want to talk about. Okay, so if we just look at this, these are some line width measurements of plasmon modes in the mid-IR. Okay, so there they are. We measured them. You can, John Cantor's done some beautiful measurements on these things using eels. Okay, so in the mid-IR, there's no radiation damping, and you're in the Drude limit, right? So this is probably the region where you'd want to look at the line widths to sort of understand that effect. So what's the point I was going to make here? Okay, so this band is the calculations of the Drude parameter for gold. At the top is Johnson and Christie's, and at the bottom is the Raschke measurements, right? So there is a big difference between those two. So I think there could be effects from the crystallinity, right? Because these measurements were done on different samples, but it's really quite hard to measure. So I guess I would like to try and do an experiment on a single crystal structure, right, to see if there's a difference in the propagation length. It's hard to make a single crystal stripe for us, right? Because we need to control the dimensions very well, right? So if you do lithography, you're automatically getting polycrystalline structures. So I think I'm dancing around the question a little bit. It could be we haven't been able to do it, right? It would be a hard experiment, but there's some possibility that you would see an effect.
Thank you. I believe Rodrigo will ask the next two questions.
Yes, thank you again, Professor Hartland, for your talk. My two questions, I'll ask one at a time just in case somebody else wants to jump in the middle. So towards the end of your talk, when we were discussing the vibrational coupled platelets, my question there was whether that avoided crossing behavior that you observed, did that change depending on the size or the geometry of the overlap region, or was that totally independent of that?
I'm going to say I don't think we have any statistics on that. I think, again, it's not really answering your question, right? But you could imagine, we didn't do this, but you could imagine doing an experiment, right, where you try to aim for the middle or the edges, right, to address that issue, right? So there must be some transition between coupled and not coupled, right? But we don't know, we didn't explore that. I think in general, right, that's pretty hard to do that sort of mapping experiment. Okay, the experiments take quite a long time, right? So if you wanted to make a map at different points, right? You got to kind of do the measurement in a different way.
Mhm.
Then this will be a hard experiment. So I would expect a transition region. I don't know if the magnitude of the coupling depends on the amount of overlap. That's kind of an interesting question. You could probably try to sort that out. You need a lot of statistics, though, right? Because you can sort of see that there's going to be a lot of noise in the data. So it's going to be a hard thing to get into. Yeah, it's interesting. We don't have any data on that. It could be.
And sort of like an intermediate question there would be, is there a way with the setup that you used for these measurements to perform the same sort of changing of the matrix where you add a liquid and look at whether having these in a different, not in air, but in a different matrix, would that affect that coupling too?
We did do that. Quite did do that. It's if you just put water on it, you do get a different coupling. I'll have to get back to you on what happened. In general, it seems, if I remember this rightly, it kind of makes it go away, the effect go away. You do get damping, so partly it's much harder to measure the frequencies, right? Because they're damped, the motion, the energy is damped away. But I think it destroyed the coupling. Now, whether they just sort of, the liquid gets in between and increases the distance, right? That could be all that's sort of happening here. I think what one ought to do is just actually calculate that. I think I know how to calculate that. I haven't done it, but that would be the first approach, right? Is to sort of do a calculation of how the coupling depends on the distance. And there is a paper in JPC on that recently, on calculating the coupling between dimers. And so that would be the approach by Aurelian Krupp from the Lyon group. So that might actually, your question might actually be in that paper.
Okay, I'll take a look. Thank you for pointing
that
out.
It's a complicated paper.
Carlos, do you want to take the next question? We have one.
Yeah, I'll ask. There's one question from the audience, and the question is: in general, do you see symmetric breathing modes in these nanoplates, and can less symmetric modes also be seen?
So for the nanoplates, we only see the breathing mode. It is possible to see modes that have that are not completely symmetric. Okay, so if you have odd-shaped particles or two particles very close together, you can start to see weird sort of other modes. So, you know, to zeroth order, it's the breathing modes, but there are tons of these modes. And sometimes if you have like a break in symmetry from the substrate, or you have two particles close together, then you can start to see other modes come out. We've only looked at single structures. Maybe Stefan can answer that question with the ring structures that he was looking at, whether you get these different, you get sort of different types of modes come out. But you can see different modes. You know what, in general, right, you have to do is you look at the experiment, and then you have to try and calculate what it was from finite element simulations and to see what you got out of the experiment, right? But there are there's, well, boy, not an infinite number, but there's a ton of these modes for any given structure.
Thank you. And Rodrigo, do you want to ask your next question?
Yeah, I'll ask my other question, and then I think we can transition. So when you were discussing the mass loading and the changes in the frequencies that you observe, my question was whether those could be sensitive enough to notice whether, instead of having a cluster of nanoparticles, if you would be able to use those for sensing, not through chemical interface damping, but for mass loading changes.
Well, okay, so the answer to that question is actually yes. People make these very high frequency membrane resonators where you can measure masses of things on the membrane. And to get that to work, you have to do it in vacuum and often at cold temperature. And you have to, you don't use optics to excite the vibrations, right? So these are slightly different experiments, but there are mass sensors based on these vibrations. Okay. The good thing about plasmonic resonators, like what we look at, is that you can excite them with light and probe them with light. So in that sense, they're a lot easier. The bad thing about it is that metals seem to have a quite large intrinsic damping of the vibrational mode, right? So if you wanted to develop them as a sensor, it's not clear that they'll compete because, the quality factors of these membrane resonators that people make are 10 to the 4, 1,000, 10 to the 4, right? So 100 times better, right? So they're much more accurate. Now, when you have these resonators, the other thing you have to worry about is where is the mass, okay? So in principle, right, you're going to get a different result in the experiment if you have the beads here, the edge of the plate compared to the middle. So you have to work out how to account for that before you can, back calculate what the mass is. So we're interested in looking at that, and trying to work that out for these plates. But the upshot is that the quality factors are not going to be big enough for metals to compete. They're more convenient to study, and so you can explore that effect, but you won't make a sensor. It just won't be. The quality factors won't be competitive with what you get out of semiconductors. Right? But you can do that, right? And so it's of interest to sort of explore that with metals. But it has been done in semiconductor land. But these are different devices, right? They're engineered devices.
We have 2 questions from YouTube, from the chat on YouTube. So I'll ask maybe the first one. And the question is it possible to fabricate refractive index sensor based on the radiation damping?
Well, based on radiation damping, well, I think yes. I would probably measure both the wave vector and the radiation damping to do that. But both those things are sensitive to the refractive index below and above the wire. So yes, you would be sensitive. You do see an effect. To go up now, in some sense, right? I kind of like in these experiments sort of said, well, we come to an end with this, right? One of the reasons we're sort of coming to an end of it is that it's not clear that we're getting better information than what you get if you just have a film and a prism, right? So then you have an SPR device, which is a refractive index sensor, right? So you could certainly do it with these stripes and looking at the radiation damping the way that we did it. But ultimately, it's not clear that it's any better than what you get out of a thin film. Okay? And a thin film is a very effective refractive index sensor. So the answer is yes, you could do that. Would you be better off than just putting a gold film on a prism? I don't know. I think you'd probably be better with the prism.
Sounds good. And then the next question, it says, naive question. Could gold nanowires be used to detect symmetries in a salt crystal matrix containing halophilic organisms?
There's no indication whether that's the vibrational mode or a radiation damping question.
No, I'm not sure I understand the question myself.
Well, I'll answer the question I want to answer, so that's fine. There is some opportunity maybe to probe viscoelastic or effects, right, or viscosity in materials, right, by looking at the damping, right. So this is a demonstration of that you can do this either by these Brillouin oscillations or by the vibrational modes in different liquids. And so you could put a cell on top of these materials and look at what happens when you have a cell, right, and get some information about the relaxation times in the cell. I'm not sure you're better off with the vibrations or with the Brillouin oscillations, right? You could do it, maybe it's a little bit easier to just do that through Brillouin oscillations. So if you have like something sitting on top of the plates, whatever this material was, then you might learn something about the material by looking at the damping of the vibrational modes. On the salt crystal question, you would, I'm not sure you get, you put a salt crystal on top of the particles, you'd get a damping, but it'd be like a solid. So, you'd measure something about the acoustic, speed of sound in the salt, but I think there's probably a better way to do that measurement.
Okay, yeah, thank you. And Rodrigo, yeah, you wanna go?
Yeah, I was gonna say, I think that now what we can do is we can ask faculty to sign off. And then if there are any students who would like to ask a question in the student and postdoc only session, then we can take those questions then. So thank you again, Professor Hartland, for such an interesting talk. And then I'll go